Okay, we've got 1:30, so why don't we get started? Good afternoon, research methods. Oh, we can do better than that. Good afternoon, research methods. Okay, there's our orienting response. Welcome to Tuesday of week number 10. Let me close the door here to get rid of some background noise. What a rowdy floor we have today. Some rowdy neighbors. Okay, so we do have a homework assignment that's going to be due on Friday, and I'll hand that out at the end of day tomorrow. And we'll get set today learning a couple of new concepts and reviewing some old ones so that you're well prepared for that homework assignment. What I thought I'd do today is start out with yet another extra credit opportunity. So why don't we have you, this will not be a pop quiz, so if you don't get this one, you're not losing any points, but this will be an extra credit opportunity. If you'll take out a blank sheet of paper and put your Slater box up top, we'll give this one a whirl too. And please take everything off of your desk. Okay, people pumped up, ready to go? Chance to earn some more points? Okay, here's our extra credit opportunity. And the question simply stated is, what is our mantra for basic ratios? What is our mantra for basic ratios? This can be done in one sentence, and when you're done, face down on the back table, please, with your response. While you're back here, if you haven't picked up a handout, please do so. We'll have a computational handout today. You can leave the perforations on there. That's all right. I'm a big boy. I think I can handle the perforations. I won't choke on them. Wow. That was a fast response. Must be a short mantra. All right. Are those all in? Okay, great. Well, look forward to getting these back to you in a speedy manner. We do like speedy feedback around here. We do like lots of it too, as you might remember from the learning component of Intro to Psych, when you learned about learning theory and operant conditioning. It really is helpful to get feedback very quickly and on a frequent basis. So we hope that that facilitates your learning. Okay, so what we'll do today is see if we can continue our conversation on independent samples designs. We were talking about ANOVAs, lots of topics within the concept of the ANOVA. And so just to get us started, I wonder if I can ask you to think for a moment about drawing the F distribution. We won't have to do this for a test question, just to get started. Can you all draw the F distribution and label it? I've had it up here several times. I've had it on at least one video, maybe more than one video. Can we draw the F distribution and label it? I'll give you this much. Okay. We'll draw the F distribution and we'll label it. Okay, I think some people look like they're finished. It's okay if you're still working. For those of you who have the basic shape, can you just draw the shape in the air? Can we all do that by gesticulation? Where's the shape going? Okay. All right, is this positively skewed or negatively skewed? Let's yell it out. Positively skewed. So that means our tail is going to go to the right. We're going to start over here just like this and over this way. Anybody want to help me out with the label on the ordinate? The label on the ordinate. Any idea about that? First, do we remember which one the ordinate is? It's been a while since we've used that phrase. Okay, let's all show by gesticulation which of the two axes is the ordinate. There, okay, right, people are going up and down. All right, that's good. So what label do we put over here? Let's yell it out if you know it. A P, okay? Anybody know what P stands for? What does P typically stand for in this class? Probability or frequency, right? Okay, that's what that is. All right, how about some of the numbers here? What range might we start out? Down on this side, what might we have? A 0. How about on the other extreme, what do we have? Yell it out if you know it. Positive infinity, okay? So I'll just put infinity. Maybe I'll label it as positive infinity. And I'll put the positive there because we do have some statistics for which that could be a negative infinity. For example, the t statistic goes off in each direction endlessly, as does the z distribution, which we call the normal distribution. Okay? Anybody have an idea about what value goes right at this modal point? Can we yell that out? 1? Okay, 1 goes on over here. All right. Let's see if we can get somebody to raise their hand and tell us what else we might begin to add to this to make it a little bit more complete. This is actually most of the way there. Anybody have? We'll go with Natalie. Thanks.
Critical value.
Critical value. Okay, and you do it like this, and I'll go over on this side. Anything else you want to tell me about the critical value, Natalie?
95%.
All right. She's pointing 95% over this way. I'll make that just a little bit longer. And 0.05 over here. And we're frequently interested in the most extreme 5% of any of our distributions. This week we're talking about an F distribution. In other weeks we might be talking about other kinds of distributions. It might be t distributions or r distributions or chi-square distributions, the normal distribution. We're typically interested in the most extreme 5%. We'll call this the critical value. I'll put that down here, crit val. All right. Where typically will the critical value come from? Anybody remember the name of the Excel command that we might use? Yell it out if you know it. Yeah, go ahead. Finv, right? So we're typically going to get any kind of critical value from some sort of an inv command. If we're doing an F test, we'd use the finv. If we're doing a t test, we'd use the tinv. If we're using a chi-square, we'd use the chi-inv. That's the pattern there. So we're going to be using the finv in this case. What should I be labeling this entire axis? Yell it out if you know it. This entire x-axis should be labeled what? What's going on down here? Was that a hand or just a, no. Okay, just a stretch. Oh, is this a stretch? This will be the F statistic. And let's see if we can have somebody recall for us. What does F stand for? Anybody recall? The founder of this, Fisher, right? Okay, so Fisher was the person who developed this for us. Okay, and then sometimes we might even put up here one more component. We might specify the degrees of freedom. And as you might remember, the degrees of freedom are twofold. I'll just make that number up. They were twofold for the F distribution. We actually have a numerator and a denominator. Okay? All right. All right. So thank you for helping me through that. Hopefully folks will get familiar with that. And I think once you draw the distribution and understand that we have statistics that are increasing from 0 in principle off to positive infinity, as we're moving with higher and higher F values, then the area to the right of any given F value is getting smaller. If we get out this far, we've divided the distribution 95% that way, 5% that way. If we wind up with some really big F value out here, we might have just something like 0.01 left or remaining to our right-hand side. Okay? And that would be something in our rejection region. And we call that value the observed value of our alpha level. So we have an observed alpha level and we have a criterion alpha level. Our criterion is always the 0.05. Okay, really good. Why don't we do just a little bit of review before we get into today's stuff. We actually completed everything we needed to yesterday in our 1028 PowerPoint, but we rushed just a tad at the end. And I hate to do that to you. So why don't we go back and just see if we can have, first, somebody remind us about two things that post hoc tests do for us. Anybody want to help us out with that? This is the very end of the 1028 PowerPoint. We actually answered this question yesterday in class. We'll see if we can get two things that the post hoc tests do for us. Natalie's got something again.
It allows us to see which pairs of means.
Okay, which pairs of means differ from each other. And I think I see Nina, were you raising your hand or no?
Yeah.
Okay, what else happens with the post hocs?
Controls or corrects the cumulative.
Wonderful. The controls are correct for the cumulative type 1 error. Thank you, Nina, and thank you, Natalie. So the idea there was on this last point that we typically have the 0.05 alpha level as our criterion alpha level, and we have to make an adjustment there for this cumulative type 1 problem. When we're doing ANOVA, we might be making many, many different kinds of comparisons. Instead of comparing just 2 means, we might be comparing a whole bunch of them. And it's almost like every time we make another comparison, we've got essentially another lottery ticket, another opportunity to get a extreme score just by chance. And we do want to keep some control on that, so we make an adjustment, we slide this thing out. Can we yell out some names of the post hoc tests? There are 3 different varieties that we had. These are last names of statisticians. Tukey? Yeah, that's how that's pronounced. Tukey, right? Anybody else? Go ahead, Nina. Dunnett and Chaffee would be our other one. And Chaffee is often considered the most conservative correction. What we mean by that is Chaffee would move this back a little bit further. And we would get into why we would actually prefer one of these versus the next if you choose to take the next stat course that we have here. But for right now, all we need to know is that we have these 2 features that Natalie and Nina have pointed out, and that is that these can be used to help us pinpoint exactly where that difference is, because the omnibus test only tells us that one of these things is not like the others. And that's all that we get out of that. And then we have to make this correction, and the post hoc test do that for us. Okay, really good. One last question that we'll do before we take a really close look at this last item, and this way. And that is, can somebody help us out with what we mean by the expression one-way ANOVA? I've mentioned it in the videos. I mentioned it once or twice yesterday. But then I think people tend to forget that. What do we mean when we say we have a one-way ANOVA? Anybody have an idea about that? A one-way ANOVA. Okay. Yeah, it's not something that we spend a lot of time on, so I'll give you this one. A one-way ANOVA means that we have one independent variable. And we've defined an independent variable before as the variable whose effect we seek to know. Okay? So we can have a one-way ANOVA. It means we have one independent variable. And that one independent variable can have any number of levels. It would have to have at least 2 levels for it to be a variable. It would have to vary between 2 states, so to speak. But it can have any number of levels. It has to have at least 2, though, to be a variable. And then we can have a second variable, or a third variable, separate and apart from how many levels any one of those variables might have. Okay? So we can have a 2-way ANOVA, a 3-way ANOVA, and those become very, very complicated. And we'll do those in a couple of weeks, but we're just going to try to get our feet wet with a one-way ANOVA. Here we have an example, interestingly enough, of a one-way ANOVA. We ended with this. We were talking about a health psychologist who might be interested in cholesterol levels. And just by a show of hands, how many people here have had their cholesterol measured in some way? A lot of young people haven't, but some young people have. Okay? I won't ask you to report what your cholesterol level is, but you can imagine that you can have your cholesterol checked, and because you're all young adults, you might wind up in our young adult group. I'm a middle-aged adult. I'd wind up in that second group, and your grandparents, my parents, would be in the older group. And we can compare across these groups, so we'd actually have one independent variable that has 3 levels. Our one independent variable would be age, and it would be operationalized, in this case, really somewhat categorically. We have a category of younger people, we have a category of middle-aged people, and a category of older people. And we're getting their means, and we're differencing those means, and we're seeing where those land. And then we're asking, are they significantly different from each other, using either a Tukey correction, and then later on in this bottom box we're using the Chaffee correction. How many people are following that so far? Okay? Anybody want to help interpret what's going on here with respect to our sig values? Can we have somebody remind us about what we said there? It's kind of a busy table, but this does come out of SPSS. Can somebody help us with that? Who's not sure how to interpret the sig values? Okay, several of us are not sure. Thank you for being honest. What we might do is look at any particular comparison. Here's way up top, we have the young people versus the middle-aged people. Who's okay with that? And what they're saying there is we'll call that first age group, if you will, age group I, and we'll call the other group age group J, and then we have I minus J. So if we do young minus the middle-aged folks, we wind up with negative 52 as our mean difference score. Okay? So let's just pause there for a moment. What would it mean if we do I minus J? What would it mean to say that we have a negative difference score there? How would we interpret that? I minus J turned out to be negative. So what do we say about that? Thanks, Jenna.
Probably the J values are going to be larger than the I values.
Okay, which would mean that the middle-aged folks have higher cholesterol levels than do the younger folks. Who's following that? Does that work for us? Okay, so we wound up with a negative number in that case. Is that number statistically significant? Well, let's see if you want to vote on this. We'll have you put up 1 finger if you think that difference is significant, 2 fingers if you think it's not a significant difference, 3 fingers if you're not sure what to do with this. So we're comparing young folks like you to middle-aged folks like me on our cholesterol counts. Is that a significant difference according to this? If you vote with your fingers, 1 is we think it's different, so we'll reject the null hypothesis. 2 is retain the null hypothesis. And 3 is we don't know. Okay? We get everybody voting, please. We'll see how folks are. Okay, so we're all seeing that we are rejecting. And so we're going to make a rejection when we compare young to middle-aged folks. How about, let's do it one more down. That was a good response. If we do young to older adults, that's the second line down, the bottom of the first box. Let's have you vote. 1 is reject, 2 is retain, 3 is I don't know. Okay? Hopefully we're seeing lots of 1s here. On the second line down, it's young versus older. And so that's going to be statistically significant, okay? And then let's see if we can take a very different one. We'll compare middle-aged folks like me to people who are my parents' age. Middle-aged versus older. We'll follow that one across. We'll have you vote. Retain is 2, reject is 1 as before, and then 3 is I don't know what's going on here. Okay, people are retaining, and that's the right idea, okay? All right, anybody want to guess as to why it is that that's a 334 and that's a 368? Anybody would have a notion about that? I don't need to know exactly the computation, but just why is this number bigger than that number? Looks like the same set of comparisons, right? We've always got young versus middle-aged and older, and then all the pairwise comparisons, right? And this is pinpointing where the differences are. Okay? And we're pinpointing either using a Tukey correction, a Tukey post hoc test, or a Chaffee post hoc test. We're getting different numbers, though, in some of these cases. Any notions about why that might be? Go ahead, Jenna.
Well, the second one, the Chaffee, is it's more conservative.
Okay.
So you're going to have like an alpha level that's more conservative than maybe 0.05.
Okay.
So that goes into the F dist.
Yeah, okay.
If you're trying to find the sig values, that's going to change the sig value.
Wonderful, very nicely laid out. So all of these post hoc tests are going to move this thing further off to the right, making it harder to beat the number to beat. First, who's okay with that much? Is that working for us? Of these, as we said a couple times, Chaffee is the most conservative. So Chaffee is going to move it furthest out this way, and that's going to make it more and more difficult to get down to a 0.05 or less. And you can see that these numbers, 0.368 and 334, are similar, but this one's just a little bit further away from the 0.05 cutoff than that one is, right? 0.368 is a little bit further away from that magical 0.05 than is this 0.334, because the Chaffee folks have moved this even further out than the Tukey folks have. How many people are following that? Yeah? Okay, and there was one hand. I think Kip had a hand.
Yeah, I was just wondering why, that doesn't explain why there's still 0.334 for the Tukey one. I'm wondering why.
Why is Tukey 0.334? Yeah. Okay, so let's take a look at where the 0.334s come up. That's actually a very good question. There is some redundancy in the upper half of this box. We can compare middle-aged to older, and when we do that, we come up with a difference of 0.334. Okay, and then over here we can compare older to middle-aged, and we come up with 0.334. So those numbers should be the same as each other. Does that much work for you? Yeah. Okay, and then also you might notice that one is negative and one is positive. We just went like this with our means. Does that work for you? Okay, so far so good? Okay, and then do we need to do something else on the bottom? We're really comparing the top box to the bottom box, and we're just saying, why is that a 334? Why is that a 368? This is a more conservative correction. Okay, really good. Okay, any other questions on this so far? There's one more thing I'd like to try with this that we didn't have time for yesterday. Okay, twice this semester, we've talked a little bit about this confidence interval bit. We spent a little bit of time a couple of weeks ago, and then we really unpacked it maybe 3 or 4 sessions ago. But they've taken all this information and they've given us just a little bit more to say about all of these. They're talking about this 95% confidence interval with the upper bound and the lower bound. First, by a show of hands, who remembers computing that before? The upper and lower bounds for confidence intervals? Okay. Anybody want to try to take a look at what you see there? You might even do something like this. You might take just the very, very top line. This is the Tukey line for young versus middle-aged. And anybody want to help us try to understand what's going on in that 95% confidence interval? It's been a little while since we've looked at this. Any words you can put around that? 95% confidence interval seems to have a lower bound and an upper bound. Okay, thank you, Kip.
You know, that saying is that they're 95% confident that the mean difference is between
Those two numbers.
the first line between -71 and 60.
Right, okay, so we're 95% confident that even if we don't know exactly where the mean is, we happen to have measured the mean at -52. Now maybe that's not quite right, but based on what we know with regard to sampling and the distribution of means and the standard error and so forth, we're 95% confident the actual mean will be no lower than -71 and no greater than -33. Notice that both of those numbers are negative, right? Both of those numbers are negative. If we draw this, and we've done this once before, we can have a zero difference. These are the difference scores. And the null hypothesis would be something like, in the population, there are no differences between young people and middle-aged people with respect to cholesterol level. So if that were true, that there were no difference between this mean and that mean, then when we subtract that, we should come up with a mean difference equaling 0. Who's following that? The mean difference should be 0. And what this thing is telling us is that the upper and lower bounds are both negative. It looks like we're getting numbers that might range from down here to maybe down here, something like that. And this might be something like -33. This might be -71. So the actual difference is going to fall somewhere in here. It's not going to fall right on that 0 line, which is what the null hypothesis is predicting. We've done that one once before. Who remembers doing something like that before? Does that ring a bell for us? Okay, really good. So hopefully now you can see some connection between the confidence intervals and these sig values, that there should be some kind of correspondence there. Okay? All right, why don't we draw the line there, unless somebody has other questions about this or other comments? No? Okay. All right, let's go ahead and we'll open up the one for today. Okay. And we'll talk a little bit about the F-table exercises that we had. Then we'll talk a little bit about F-ratios. We won't actually do the computations today, but for some of the information that we need, I think this handout will really help you. Okay, so we have our F-table. And we'll see if we can really understand this. And as we did in the video, we have a series of questions associated with these F-tables, and we'll see if we can really understand them inside and out today so that we can set up our computations really well for the rest of the semester and really engage in some good quantitative reasoning for any kind of research design that we might have that's suitable for a independent samples ANOVA. Okay? So here's our F-table, and we have this question for us: what are the other names for these kinds of terms? I'm calling them group and error. Anybody want to help us out with what else we might call these? Group and error. Okay, thanks, Catherine.
Group is called the between groups, and error is the within groups.
Okay, so between groups and within groups, and it's between group variability and within group variability is what we're talking about. And I think I saw Sasha's hand and Katie's hand. Were you going to say the same thing? Okay, yeah, thank you for that. And thank you for your quick response. It looks like people may have really tuned in on this thing. Okay, let's go to another one. I have several F-tables throughout this presentation with canned responses here. We'll see how people do. According to the F-table, that's how each of these will start out, should we reject or retain the null hypothesis here? What do we think? Let's all yell it out. Reject, and why is that the case? Okay, really good. So we're going to be way out here somewhere without actually saying, oh, here's our F value. 7.82 is where that is. That's way out here. So only something like 0.002% is out this way, right? And then whatever the rest of that is, 0.998 is that way. Okay, right? So it's a really big F, and as F is getting bigger, this observed alpha level is getting smaller. Okay, those two are inversely related to each other. Okay, really good. Let's go on with our next one. According to the F-table, does this study have validity? Okay, anybody want to help us out with that? Does the study have validity according to the F-table? Okay, we'll go with Katie this time.
This table, there's not enough information to talk about validity.
Okay, right. We don't have enough information in the F-table ever to tell us about validity. Can you say anything more about that?
Well, if you wanted to look at validity, you would have to look at the Levine
Actually, you could look at some other information to get to validity. You probably wouldn't use Levine. That tells us about equal variance. Okay, but it's good of you to point out that we can't get to validity here. Anybody else want to say anything that they recall about validity from here? Okay, thanks, Jenna.
Well, validity is that's kind of a generalized term. Validity is more complicated because you have internal and external
Okay. Yeah, right. So there are different varieties of validity.
So to say if it has validity isn't really a question that's
Good, okay, right. So that's actually a very good objection. So the question, does this have validity, is actually a relatively general question because now we're further into the semester. We know that there's internal validity, there's external validity, there's convergent validity, there's discriminant validity, okay? Lots of different kinds of validity there, none of which can be answered just by the information in the F table. We need to do some other kind of investigation. Okay, really good. Okay, according to the F table, how many groups were there? I'll let you raise your hand if you think you know the answer to this one. How many groups were there? And I'll give you a little clue. If you're not entirely sure, you can take advantage of this. You might be able to surmise it this way, but I think I saw Marin's hand, and then I think I saw Giselle's hand go up next. Go ahead, Marin. There were 4 groups, okay. Giselle, is that what you were going to say? Yeah. Okay, very good. So we have 4 groups. Could either of you, Marin, can you tell us how you came to that conclusion?
The degree of freedom is the number of groups minus 1.
Okay. Okay, right. So we have 3 degrees of freedom shown here, and frequently it's the case that degrees of freedom are always some number minus 1. Occasionally it will be some number minus 2. In this case, it's some number minus 1. The number of groups minus 1 equals 3, so there had to have been 4. Was that your reasoning also, Giselle? Okay, thanks very much. So there were a total of 4 groups in this particular case. Okay, so this would be a one-way ANOVA. And again, why is it still a one-way ANOVA? Somebody remind us. We said it earlier. There's one independent variable, and it has how many levels? 4, because we have 4 groups. Okay, so we have the control group, and then 3 different varieties of experimental group. Okay, but we have one independent variable with 4 levels. Okay, let's go on to the next one. How many participants were there in each group? Anybody help us with that? Mira's got it. Okay, thank you, Mira.
There were 5 people.
Okay, there were 5 people in each group. That's exactly right. And that took just the arithmetic wasn't really hard, but it did require a little bit of quantitative reasoning. Can you walk us through?
Well, it's the total of observations minus the number of groups, and so there are 16.
Okay.
16 plus 4.
Okay, right. So we should put a couple of things together there. So what's interesting is the F table doesn't tell you that explicitly, so to speak, but we can derive it. The same thing was true for the number of groups, right? We can derive the number of groups based on what we know about how these things are computed. Also, we can see from this that capital N, which refers to all of the participants in the study, not just the number in one group, but all the participants are going to be represented by capital N minus A, which stands for the number of conditions. So 20 minus 4 would get us to 16. 20 must be the total number, and that would mean that if we had 20 people and we had 4 groups, there would be 5 persons per group. Who's following that? Okay.
Sorry, I'm not.
Okay. All right. So can you tell us where we didn't quite follow that?
Where do you get N?
Okay, good. Really good. So first of all, here, if we look on the degrees of freedom up here, we can see we've got 16. So far, so good. 16. Okay. So that's a little clue for us. And if we look at this formula, you see that we have capital N minus A. Does that work for us? Capital N minus A is the degrees of freedom for the lower of the 2 rows here, which we mentioned was our error term, also called our within subject variability. Does that work for you, Katie? Okay. All right. So now we know that something N minus A is equal to 16. A moment ago we said that A was 4 because we had 4 groups. Okay. So some number minus 4 gives us 16. That brings us up to, there must have been 20 people overall. So far so good? Yeah. Okay. So if there are 20 people overall, and we have 4 groups, how many people do we have per group? Does that work? It works out to be 5? Yeah. Okay, 5 per group. Okay. Actually, that turns out to be, and I usually like to use that example because that's what we have in this room. Throughout this semester, I will frequently be coming back to an example where we're talking about whether Prozac works or not, and we'll assume that we have 0, 1, 2, and 3 milligrams of Prozac in our experiment. We have one independent variable, which is your Prozac level. It happens to have 4 levels. Okay, and in this particular room, we have 20 seats, 4 sets of 5. Okay, all right, let's go on to another one. According to the F table, which groups, if any, differed significantly from each other? Anybody help us with that? So we have 4 groups. Which groups, if any, differed significantly from each other? Okay, thanks, Natalie.
You can't know that exactly.
Okay.
It tells us that there's one that's different from the other, but it tells us.
That's right. Very nicely stated. So this table tells us that there is a difference somewhere, and we know that because we're rejecting the null hypothesis. What it doesn't tell us is whether group 3, if you will, is different from group 1, or if group is 2 is different from 4. It doesn't tell us where that is. We would need post-hoc tests to tell us that. But we know we have at least one difference. We might have more than one difference, but we have at least one. Okay? All right, really good. According to the F table, which was greater, the variance between groups or the variance within groups? So that's a binary question. Either between was greater or within was greater. Let's all yell it out. Which one was greater? Between? Okay, I was hoping for a bigger yell than that one. I was hoping this one was really, really obvious. Maybe somebody can let us know why between is greater. What information did we pull out to come to that conclusion? We're looking at the variances, okay, right? And the mean square really is a variance. Okay, and we said the top, I think it was Catherine who said the top line was for between variance and the bottom one was for within variance. So we have 18 versus 2. So that's one of the ways of thinking about that. There's another way of doing that too. Let's say I didn't show you the variances and I only had this half of the table. Right? I only had what is your right-hand half of the table. Can anybody tell us how we might have been able to figure out that the between group variance was larger? Do you want to help us, Jenna? Thank you. Yeah, yeah, well done. Okay, so this is, we call this the F statistic. We sometimes call it the F ratio, and it's always the ratio of the between subject variance over the within subject variance. And whenever that number is greater than 1, that means that our numerator is bigger than our denominator, so our between group variance would have to be larger than our within group variance. Who saw that, follows that logic for us? Okay, if we remember that this F really is a ratio, then that will help us along quite a bit. Okay, according to the F table, was the homogeneity of variance assumption satisfied? So you can help us with that. Let's do it this way. We'll have you vote with your fingers. We'll say 1 equals yes if you think yes it was satisfied. 2 equals no it was not satisfied. 3 equals some kind of question mark. Which of those best describes? Sasha's got 3. Okay. Is it because you've got a big, you're not sure why, or you don't like yes and no very much? You're not sure why that's the case, okay? Let's see who else. Anybody want to help us with that one? Can we go with Meg if that's okay? Oh, I'm sorry, Katie. I pointed to where Meg used to be. I'm sorry, Katie. Thank you.
You can't tell.
You can't tell. That's right. You can't tell from this. And what piece of information would we need? We need Levine this time. Thank you, Katie. Okay, so we would need Levine to tell us about the equal variance. Okay? And we don't have that information here. All right. All right. So now what we'll do, maybe we'll have you break into Excel if you think Excel will help you. We'll do a few more of these, and we'll have you actually make some computations. What I did hope that you enjoyed about that was what we're finding out here is what kind of information really is in the F table, what information isn't there, and what information could you surmise. So for example, we were able to surmise how many people there were per group, even though that number isn't explicitly represented there. That answer was 5. 5 doesn't appear there directly, but we could pull it out. Other kinds of information you just can't pull out. You can't pull out something about validity. You can't pull out something about equal variance here. So we're really coming to understand what information is there. Okay, how about we do it this way? I'll let you go into Excel if you like. I'll leave this up here, and we'll have you fill in the blanks as we did in the video. We'll have you report to us what kind of information is available or is missing by the question mark. Okay? And then if we need me to exemplify that, I'll do that. But we'll give you a moment to work with this in Excel and see if you can fill in that question mark. Still working with the F table. This is still our underlying distribution. We're always trying to figure out where do we land on that thing. If you do come to an answer, I wonder if you can raise your hand so I can see where people are. Okay, a few folks have that. I wonder if we can go with Giselle again. Can you tell us what number you came up with? To the negative fifth. Okay, 3 point something times 10 to the negative fifth. Can I abbreviate it that way? How many people got that number? Okay? And can you just remind us how you did that, Giselle?
I did equals of this,
Okay?
and I put in 14, 3, and 21.
Okay, thank you. So you went equals fdist. And this is cool because when we're doing fdist, we're now trying to find the observed alpha level. And I don't have it up in front of me. Can you remind me what those numbers? Those were, you said you just put them in 14?
14, 3, and 21.
Okay, 14, 3, and 21. Okay? And we come up with something like that. Okay? All right, first, how many people see where that number came from? Is that working for us? And that we use an inv command to get the number down here, this f statistic. And we use the dist command to get the equivalent number expressed as an alpha level, at the observed alpha level. Just like we said a few times, we can express any number by its z-score, we can express it by its raw score, we can express it by its percentile rank. When we use the dist command, we're getting some kind of observed alpha level. When we use an inv command, we're getting the actual f statistic itself. And those two numbers will always be inversely varying with each other. As the f is getting larger, this area to the right is getting smaller. And now we're down to a really small level. Who's okay with e to the negative 5? Are people following that? Okay. All right. So that would mean that the actual p-value here would not just be less than 0.05. It's actually something like 0.0000003 and some change. Hope I got that as the right number of zeros. But we have to move that over now 5 times to the left. Okay. All right. You stay there in Excel. I'll give you the next problem so we can parallel process. Okay. Yeah, this is the one we want to do next. Okay, we'll have you take a look at this and see if you can fill in those numbers. Okay, and I realize some people have already maybe plugged away on this. Does somebody want to help us out with what they've got in this case? Why don't we go with Catherine and then with Maren this time?
So for the first two
Okay.
question marks, what you do is you look at the total number.
Okay.
And you just subtract the total number from the between groups and get the within groups.
Okay.
They're both 7.
Okay, so we're going to get 7 here, and we'll happen to get 7 here. And then you want to help us out with that last one?
Yeah, so for the mean square, you just divide them by each other. So 7 divided by 7, and you get 1.
Okay, and if I can put up one formula here that I hope you'll all recall from maybe the first week of class, that we said that the variance, maybe you can help me. How do we define the variance? The variance computationally is, and actually Catherine just did it for us. How do we, so the mean square actually is a variance, and you were correct when you said,
SS divided by df.
okay, right, that's SS divided by df. Sorry that my item is dying on me here. SS divided by df. All right. Okay, so then we have 7, 7, and 1. 7 over 7 is going to give us 1. Okay, and that should make sense also because we have a 17.5 there. And the F ratio itself, excuse me, the F ratio would have to be mean square between, whoops, mean square between over mean square within. 17.5 over 1 would give us 17.5. Okay. All right, let's go on to one other one. Can we yell out what this, maybe you've already recorded what this answer is? Yell it out if you've got it. Okay, yeah, it looks like Katie's got it, okay, and that was 3.3 repeating, thank you. So that's 5 over 1.5, okay? Mean square between over mean square within. A mean square is a variance, and the variance is defined this way, SS divided by df. Let's go on to another one. Why don't we yell these out if we've got these? 200, 900, and 1100, just in case you wanted to complete that. And can somebody walk us through where that came from? How did we come to that conclusion? Okay, thanks, Maren.
The mean square times the degree of freedom.
Okay, right, so we can do the mean square times the degrees of freedom. Remember that the mean square actually is a variance. We can multiply that by the degrees of freedom to recover the SS. I can basically spin this thing around. I can multiply each side of this equation by the degrees of freedom, and I'd have df times variance, which is mean square over here, equaling SS. Okay, so that works as well. All right, really good. So I think people have a good feel for all of that. Any questions on F-tables before we go on and talk a little bit about basic ratios? Please, Kip has a question.
Specifically about F-tables, but I had a question during the video. You said that F depends on the normalcy assumption.
Yeah.
And I was wondering, like, why does it depend on the normalcy assumption if it looks like that? It's not a normal distribution.
Thank you, thank you. So we need to understand what is normally distributed and what is not normally distributed. When we say that the F value has, the F statistic requires a few assumptions. We're talking about actually the data that we might use to analyze the F. So I wonder if I can dial down just to show you what some data might look like. Here's some data. Okay, let's say we have 3 groups, and these aren't really representative of cholesterol levels. We'll pretend for a moment that we're expressing cholesterol in these single-digit numbers. You wouldn't typically, but we'll pretend that. Okay, and we have young people like you in group 1, middle-aged people like me in group 2, and like my parents in group 3. These are the 3 different cholesterol groups that we have. So Kip's question is all about this equal variance assumption. What exactly has to be equal in variance? What has to be normal in distribution? Right, and that's really the heart of your question. What we're saying is, if you were to take the group 1 data and put it into a frequency plot, that needs to be Gaussian distributed, okay? And group 2 needs to be Gaussian distributed, and group 3 needs to be Gaussian distributed. Okay? They all need to be Gaussian distributed. Otherwise, we've violated one of the assumptions. Actually, once you start having great departures from a Gaussian, then the means are not particularly informative. Okay? All right, so we want to make sure that those are distributed in a Gaussian manner. The F statistic itself is some other ratio. That ratio is the mean square between over the mean square within. And if you plot those, if you were to run thousands and thousands of these, those would actually form a plot that would be skewed. So the statistic itself has this kind of distribution, but the data that you would be using for analysis, or the data that you would be analyzing, would have to be Gaussian distributed. So there are 2 different populations of numbers, or 2 different groups of numbers, I should say. Does that help? Okay, great. Good question. All right. All right. Anything else on F tables before we go on to talk a little bit about basic ratios? Anybody want to help us with our mantra for basic ratios, even approximately? What is our mantra for basic ratios? Kip's got it again. Basic ratios help us compute the sums of squares. I'm going to dial back and go backwards by just a couple of slides. Look, we've been doing all of these F ratios, right? And in order to get the F table going, we always start out with the sums of squares. In these introductory exercises, I've been handing you an F table, right? But if we really did have a raw data set, where would we get the sums of squares? From yesterday's conversation, you remember that we can think of these sums of squares conceptually as being this big pie of variability that we can divide green versus red, between versus within. Okay? But where do those numbers actually come from? I think it was Natalie who asked, how do we go about getting these sums of squares, right? Or how do we go about determining what the variance is between versus within? We know that we want to partition, but how do we go about doing that? And so one answer here is that we're going to be using basic ratios. And the basic ratios are again on today's handout. We won't have time to, we still have about 10 minutes, but we won't have time to do an involved computation here, although we will tomorrow and on Friday. We'll start getting into actually doing these computations. And so we're going to use the basic ratios to help us get the sums of squares. And if we have the sums of squares, then we can engage in this really trivial kind of a computation like n-1 or a-1 to get a degree of freedom. And then I think it was Catherine who told us to go SS divided by DF will give us the variance, which we also call the mean square. Those words are used interchangeably. And once we have a mean square, then we can just take our ratio. From the first week of class, we promised ratios, ratios, ratios. We'd have an F ratio. We'd put it in context, and we could evaluate whether there are group differences, for example, in cholesterol. Okay? But to get that whole ballgame rolling, we need to somehow pull out these sums of squares, and this is a formula that will help us do it. Who's following that? Anybody have a question about that? Why we're bothering with this computation? Okay. All right. So we then have these basic ratios, which have these somewhat arbitrary capital letters that are put in brackets, and we have some order of operations. That will be one other question that I'll have for us. Anybody have an acronym for the order of operations that we'd be using for any Yeah, go ahead, Mira. Okay, please excuse my dear Aunt Sally. How many people had heard of that in high school? Is there another variation on that? There are probably several others. You know, it was always please excuse my dear Aunt Sally. Okay, all right. So that's our order of operations. And that can get a little confusing, and sometimes inside of a SPSS quiz or Excel quiz, people will do this in the wrong sequence. I promise you that you will not have to memorize these. These will be given to you, okay? I've been doing this, I'm embarrassed to say, this actually is my 20th year. I went to graduate school in 1993. I realized some people in the room weren't born when I was headed off to graduate school, and I've been using this since that time, and I've not memorized them, and I don't expect you to either. But I would like you to memorize how to work with these if you have the formula right in front of you. Okay? So just to go over that a little bit, we're going to be doing a lot of this. We'll start out with some kind of raw data set. These are the data that you're going to collect. And I hope that either tomorrow or Friday we'll run a little experiment in here and we'll get some raw data ourselves. Just like we measured M&Ms, we measured each other. We'll have a computer-based experiment on something called CogLab, and we'll see what your reaction times look like to different kinds of stimuli, and then we'll run some ANOVAs on that stuff. So we'll have a few different conditions that we might be running. Okay? And what we're going to do is have that all in Excel, and then we copy that structure down and we get a squared version of what we have up top here. So this is a squared that. How many people are following me on that? This bottom structure is the same size in number of rows and number of columns as that, but we're just squaring everything in there. Okay, and once we square everything, then we engage in this kind of formula. We sum the individuals' squared scores, square them first, and then sum them is the idea. Okay? So we take a sum of those, and that will give us quantity y. We can do this for a. Okay? We can now have a same set of scores. Okay? And we're going to need to take some column totals. Here we have a column total of 32. In this particular case, we'll square that. We'll do the same thing here and here. And then we'll add up all of those squared column totals, and we'll divide by lowercase n, which is the number of participants per condition. And I would ask you to think about that. Here you can see on our formula that we have for A, that we have a lowercase n, and that's going to mean divide by the number of subjects per condition. And I believe it says that in there, but I want to emphasize that because something like 10 to 20% of the students will divide by capital N rather than lowercase n. You will come up with the incorrect number. Okay, so we'll get some practice on that. Okay, and then we also have this grand total, and this is going to be our t basic ratio. We'll take the grand total squared, and we'll divide that by the total number of scores. And the total number of scores that we have would be the number of conditions times the number of persons per condition, okay, which is lowercase n. So here's that. We're back to our groups again. We might have had a grand total of 92. We'll square that. That works out to be 8464, and we'll divide that by 18. And where that 18 came from is we have 3 groups and 6 persons per group. Okay, so that's how we're going to have that. And once we have those ingredients, we're going to cook up with those ingredients some sums of squares. And the sums of squares will look like this. So this should be very familiar to you structurally now. You got to be really good by using all of those components. And now we're just going to take the basic ratio A. We'll subtract from that t. That will give us the sums of squares for the between groups component. And then our error term for the within conditions variability will be y minus a. Really simple formulas for the degrees of freedom. And away we go for our mean square and our f. Okay? Who's following all of that? Pretty cool. Okay, so we've laid it out computationally. We've gone from just understanding that there is this big pie of variance, and we can try to analyze the variance, and we do an analysis of variance when we're doing an ANOVA. For this introductory week, we're just doing a one-way ANOVA. We have one independent variable. It might have 2 levels, 3 levels, 4 levels, 120 levels, but there's only one independent variable. And we can take the total amount of variability as referenced by this SS, and we can begin partitioning it into between and within subjects components, and we can get an F value, and we would know whether to reject or retain the null hypothesis. Okay. All right, let's see. We'll pause this for a moment here. See if anybody has any questions or comments. Okay, why don't we do it this way? We are at 2:18. I usually go exactly to 2:20, but you've been such a good audience that we'll give you 2 minutes off for good behavior. Okay, time off for good behavior. When we come back tomorrow, we'll be doing some computation, and we're right on track with the syllabus as we've been all semester. And so please read up in your book on SPSS, what kind of computation we might have, and then tomorrow we'll do these in SPSS and or Excel. Okay? All right, hang on to your sheets, please, because when we do this in Excel, you're going to need this. I will too. See you tomorrow. Maddie, I noticed you had your hand up a couple times. I think I didn't quite get to you, so I apologize for that. I think you raised your hand once or twice, and I think I didn't quite make it around, but thank you.
like in his
It was
mind.
mine coming later than hers. So it was like, yeah.
Okay, Kip, go ahead.
Okay.
I'm going to turn myself off.